Hi everyone, myself Nithin Heraje, Assistant Professor, Department of Computer Science and Engineering, AJ Institute of Engineering and Technology, Mangaluru. In this video, I am going to discuss about curves from Module 5 of Computer Graphics. So first, let's discuss what is curved surfaces. Uh, Sometimes it is required to generate curved objects instead of polygons, right? So till now what we have seen is we could generate polygons, but how about when you want some curved objects? Okay, so for this, getting this, we have two forms, that is either parametric form or non-parametric form. So what's parametric form is if the object description is given by the dimensionality parameter. Okay, then it is called as in parametric form. So it's something like this. See, the curve is equal to xt comma yt, where x and y are the coordinate xy coordinates. X of t, y of t is the coordinate function. Okay, and if in case if it is a 3D, or if the object is in the space, then you have this equation, that is ct equal to xt comma y of t comma z of t. So the original is this z axis, that is the z coordinate function. Okay, a parametric curve is defined by polynomial coordinate function, which is called as polynomial curve. Okay, and the degree of polynomial curve is that the highest power of the variable in that function. So now let's see what is non-parametric form. If the object description is directly given with the coordinates of a reference frame, that is directly the value of x, y and z, then the representation is in terms of non-parametric. Okay, and the form is something like this: f1 of x comma y comma z equal to 0, or z equal to f2 of x comma y. Okay, so for non-parametric, the curve has the form like c of t equal to t into f of t, or c of t equal to g of t comma t. Next, going to the quadratic surfaces. So we might have spheres, ellipsoids, tori, paraboloids and hyperboloids. So we'll look into it one by one. This is in case of a sphere. Okay, so this would be the r value, that is the radius value, wherein this is z axis, x axis and y axis over here. This is a point with the coordinate value x, y and z. So this is the angle phi, which is got after this line over here, which is of 90 degree towards this r, and this gives you the value of theta. Okay, so let's check with this. Spherical surface with the radius r on the coordinate origin is defined by x, y, z points that satisfy the equation x square plus y square plus z square equal to r square. Okay, so the spherical surface in parametric form using latitude and longitude angles would be like this, that is x equal to r cos phi cos theta, where phi ranges from pi by 2 to minus pi by 2 to plus pi by 2. Y is r cos phi sin theta, and z would be r sin phi. Okay, please note down these equations for sphere, and it's a parametric form. So alternatively, you can write the parametric equation using the standard spherical coordinates, where phi is specified as the co-latitude. So that is, this would be the phi now, not this. Okay, so the angle has been changed over here. Next is this ellipsoid. If you look at this, so you have this ellipsoid, which is nothing but it seems like the sphere is just extended quite, wherein you have three r values with the different values of r. So this would be the origin of the coordinate. Origin of the coordinate is the center point of the ellipsoid, and this length would be radius with respect to y-axis, that is ry. This would be radius with respect to z-axis, and this would be the radius with respect to x-axis. Okay, and the Cartesian representation is given like this. You have x by rx the whole square plus y by ry the whole square plus z by rz the whole square equal to 1. Okay, you need to remember this Cartesian representation of the ellipsoid, right? Next is torus. So you can see that torus, this is the top view of the torus, and this is the side view. This appears something like donuts. So this is r axial from this origin 0 up to this point. This is r axial, and this is y axis, this is z axis, where x axis is 0 in side view. If you look at this figure, you can, that is the top view, you seems to have two circles here. Okay, this is the origin, and this is this point x, y, z inside the torus. Okay, so the equation for the cross sectional circle shown in the side view is given by, that is for this, that is y minus r axial into 2. So this is r axial, y minus r axial into 2 plus z square, y minus r axial square it is. Okay, y minus r axial square plus z square equal to r square. Please note down this equation also. Next is open GL quadratic surface and cubic surface functions. So with the glut functions, we can display sphere, cone, torus, or teapot. Whereas with the GLU functions, you can display sphere, cylinder, tapered cylinder, cone, flat circular ring, or you can have a hollow disc and a circular ring. Okay, something like a disc. So this is the function for a sphere, glut wire sphere. If you want a wired sphere, then you have to go for this, or if you just want a solid sphere, you can go with this function. And these are the parameters: r, n longitudes and n latitudes. So where r is the sphere radius, and n longitudes and latitudes is number of longitude and latitude lines to approximate the sphere. Okay. Next is to draw the cone. So that is using glut wire cone. Even here you can have either a wire cone or a solid cone. So wire cone R base. Uh, so the radius of base radius, the height, and again n longitude and latitude. And for the solid cone also all the parameters will remain same, where r base is the radius of the cone base, and height is the height of the cone. Okay. Then again longitude and latitude are assigned integer values which specify the number of orthogonal surface lines. Next you have is torus. So the function is glut wire torus. Again here you can have wired torus or a solid torus, and these are the parameters: r cross section, r axial, n concentrics, and n radial slices. Even here you will have the same parameters, where r cross section is the radius about the planar z axis, which is r axial, which is the distance of the circle center from the z axis. And n concentrics specifies the number of concentric circles, and n radial slices specifies the number of radial slices. Next, this is for the teapot function. Again, you can have a solid teapot or a wire teapot, and you just have to mention the size of the teapot over here as a parameter. Next is quadric surface functions. So we'll see how a quadric surface can be done using GLU functions. So first you need to assign a name to the quadric, then activate the GLU quadric renderer, then designate the values for surface parameters. So this is how that is done. These are the steps done for that. Just go through it, and you have the respective parameters mentioned over here. Okay. So that's the same. If you look at this, you can this is drawing the cylinder using GLU. Okay. So here you need to give the quadric name, and you have a R base and R top, which is the thing you need to concentrate. So if R base and R top remains same, then you are going to get a radius. I mean the cylinder. Okay, this is the radius on the base and radius on the top of the cylinder. So if both are same, then you are going to get a cylinder. And if you are having R top as 0 and some value with R base or vice versa, you are going to get a cone. Okay. Next, this is the function to draw the disk, that is GLU disk. The ring name, R inner, R outer, N radii, and N rings. So the values of inner radius and outer radius need to be given, which is nothing but R inner and R outer. So if R inner value is 0, so the radius of the inner disk is 0, then the disk becomes solid. Otherwise it is displayed with the concentric hole. And the disk surface is divided into set of facets with the radii, N radii, and N rings. Next, moving to the Bezier spline curves. This is a quite important topic. Okay, which was developed by the French engineer Pierre Bezier. Uh, so these are the some of the concepts on Bezier splines. We'll look into it, what it is. So coming to this, so first consider the general case of n plus 1 control point position. So before getting into this, first let us see what is this control points. So looking at this P naught, P1 and P2, there are three control points over here. Okay, each points are in different places. There will be a line drawing from the first point to the end point, say P0 to P2. So you have one more control point called P1 over here. So what this affects is, if it is a straight line, then it looks like this. Okay, only two control points, then it appears like a straight point. Now there is a third control point over here, so this line will be made like this. That is, this P1 will pull the line. Okay, something like a rubber band effect. So when this P1 pulls this, you get a curve like this. Okay, so this curve has three control points, wherein this curve has four control points. Okay, so in general case of n plus 1 control points, so denoted as pk equal to xk, yk and zk. So this is a point with x, y and z values, where k ranges from 0 to n. Okay, so these coordinate points are blended to produce the following position vector p of u, which describes the path of approximating Bezier polynomial function between P0 and Pn. Okay, so this is that vector P of u you are going to get, and this curve is blended with these three control points. So this is the equation that you need to remember, which is important. P of u equal to summation of k equal to 0 to n pk, Bezier of k comma n of u, where Bezier of k comma n is that Bezier of k comma n of u is equal to c of n comma k into u power k into 1 minus u into 1 minus u power n minus k. If at all you need to know the derivation of this, so we have a separate video for this, so wherein the derivation for this equation is given. You can just go through it. Where c of nk is nothing but n factorial divided by k factorial into n minus k factorial. Set of three parametric equations for the individual curve coordinates. So this is if you want for individual coordinates. Okay, that is with respect to x, y and z, you have these three equations. Just go through it. So these are the different curves using different number of control points that are used here. Three control points, four control points, even here four, and here it is 5 control points. Going to the properties of Bezier curves, there are two properties. So the property 1 is nothing but the curve connects the first and last control point. Thus, a basic characteristic of Bezier curve is that P of 0 equal to P0 and P of 1 equal to Pn. Okay, so the values for the parametric first derivatives of a Bezier curve at the endpoints can be calculated by the control point coordinates as p dash of 0 equal to minus n p naught plus n p1, p dash of 1 equal to minus n p n minus 1 plus n into pn. And the second derivatives for the Bezier curve is calculated with this. Okay, just have a note of this, how to calculate a p double dash of 0 and the p double dash of 1. The property 2 is this. If the Bezier curve lies within the convex hull of the control points, this follows from the fact that the Bezier's blending functions are all positive and their sum is always 1. Then the equation summation of k equal to 0 to n Bezier of k comma n of u is equal to 1. Okay. These are the other properties. You can just have a look at this. So this is the equation for Bezier surfaces. The parametric vector function for the Bezier surface is formed by the tensor product of Bezier blending functions. So the Bezier functions with which is occurred or which we get through blending it is this: p of u comma v equal to summation of j equal to 0 to m and summation of k equal to 0 to n p of jk of Bezier j comma m of v and Bezier of k comma n of u. Okay, so this is for finding the Bezier surfaces with the p of jk specifying the location of the m plus 1 by n plus 1 control point. So this m plus 1 n plus 1 will see what it is. So if you look at this, this is a 3 cross 3 control points, that is total of 9 control points. You can see 1 2 3 number of rows and 1 2 3 number of columns. So this is a 3 cross 3 control points where you get the Bezier surface like this. Okay, wherein if you look into this, here you have a 4 cross 4 mesh, that is 1 2 3 4 number of rows, 1 2 3 4 number of columns. So this is a 4 cross 4 control points with which you get the Bezier surface. Okay, so this is about curves. All right, that's it. Thank you. Thanks for watching this video. If you like, please click on the like button. Thank you so much. Thanks for watching.